Alright, so we will now take a look at two types of threads, user threads and kernel threads. So if you remember in one of the previous segments, we saw about the user mode and kernel mode of the US. So we saw that in the user mode, your process performs whatever it has to be performed, it is executed. But when there is some privileged instruction, something which is going to change sensitive configurations, such instructions can only be accessed in the kernel mode. So we even saw this example of guest user versus admin logging into a system, right? So the same idea of modes extends to threads also. So user processes execute in user threads, kernel processes are divided into kernel threads. The idea still remains the same. So we saw that kernel processes have little more privileges as compared to user processes. The same thing applies here as well. Kernel threads are more privileged than user threads. So when a user thread wants to perform some sensitive task, or it wants to change some important configuration, it needs to take the support of a kernel thread. So the same idea of user processes, kernel processes extends here as well. So multi-threading may happen in different ways, many to one, one to one, many to many. What is this talking about? How the user threads are mapped to the kernel threads. So we will take a minute to go back and look at the user process, kernel process thing. So there is a user process, it is executing, it realizes that some sensitive task needs to happen, it gives the system call. Then the system goes into kernel mode and that sensitive task is executed in the kernel mode. Then control shifts back to user mode and the remaining part of the user process is executed, right? So what's happening here is you have a user process, it is running as usual, and then when some privileged instruction has to be executed, the user process enlists the help of a kernel process, right? So every user process is mapped to some kernel process whose help it will enlist when it needs to execute a privileged instruction. And obviously processes are divided into threads, so the same idea extends to threads as well. Every user thread is mapped to a kernel thread whose help it will take when it needs to perform some privileged task. That mapping is what we are looking about, many to one, one to one, many to many. And when I say something is mapped to something, the left hand side talks about the user threads, the right hand side about kernel threads. So we will look at these mappings in detail now. The first is many to one, many user processes or many user threads to one kernel thread. Please remember that the left side is always about the user level threads, the right side is about kernel level threads. So these are different systems of mapping. They just define how many user threads are linked to how many kernel threads. So the first type of mapping we are seeing is many to one. Many user threads are mapped to a single kernel thread. So there are these 4 user threads here in the diagram. All of them are linked to this kernel thread. So what this means is, if any of these user threads wants to execute a privileged or a sensitive instruction, they will enlist the help of this kernel thread. So what is the benefit of this method is it is efficient. So for all 4 of these threads, this one thread is sufficient to take care. You don't need 4 separate kernel threads. In that sense, it is efficient. But the problem is, if this kernel thread gets blocked for some reason due to some error, all 4 of these are stranded. So none of these will be able to execute their privileged instructions. Also, only one user thread can access the kernel at a time. So all the others are forced to wait. So let me recap what is happening here. We know a user thread needs the help of a kernel thread to execute in some situations. We are seeing how many user threads can be mapped to how many kernel threads. There are different ways. The first one is many to one, many user threads to one kernel thread. So the pro being, for 4 user threads, it is sufficient to have one kernel thread. So you don't need to create 4 separate kernel threads here. Everything will have its own register, own stack. That memory space you are saving. But there are 2 problems. One is, if this thread gets blocked, if there is some malfunctioning in this kernel thread, 4 user threads are going to be affected. That's one problem. The other problem is, a kernel thread can only deal with one user thread at a time. So like I said, any unit of CPU can only deal with one unit of task at a time. So if 2 of these user threads need the kernel support at the same instance, one of them is going to be forced to wait. That's the problem with many to one. So we came up with something called the one to one, which, as the name suggests, means for every user thread you have a separate kernel thread. So the idea is more concurrency in the sense that if this user thread needs kernel support, it will ask the kernel thread corresponding to it. So if two user threads need support at the same time, they will ask their respective kernel thread, so nobody has to wait for another thread to finish. So in that sense you have more concurrency, first point. Second, blockage of a kernel thread leads to only one user thread being blocked. So in the previous one we saw that if that one kernel thread gets blocked, all four user threads are in trouble, right? Here that's not there. If this particular kernel thread is blocked, only this one thread is going to be in trouble, everyone else is going to work perfectly fine. These are the pros. But again, you need as many kernel threads as there are user threads, which means you are creating a large number of threads, which means there's going to be a lot of space, memory allocation. That is the overhead. That is about 1-to-1. So we saw that there is many-to-one. It has its own pros and cons. 1-to-1 overcomes the cons of many-to-one, but this has its own set of cons. So we came up with something called many-to-many, which is sort of bridging the gap between both. As the name suggests, many user threads are mapped to many kernel threads. The number of kernel threads is less than or equal to the number of user threads. This is the norm we generally follow. Now, any of the kernel threads can support any of the mapped user threads. So if this thread needs help, it can ask any of these three. If this one is working with something else, this can go over here. If this one is also occupied, this can go over here. So because of this, that waiting problem which we saw in many-to-one is, to a great extent, it is removed. So only if all the kernel threads are occupied, a user thread which needs kernel support will have to wait. Otherwise, if the first one is occupied, this can ask the second one or the third one. So in that sense, the waiting problem is removed. So you have more concurrency. Also, if one of the kernel threads encounters some problem, these can still work with the remaining. So that issue which we saw in many-to-one is also overcome. And you don't have to create so many kernel threads here, like 1-to-1, that was the problem, right? Too many kernel threads. That is also not here, because generally the number of kernel threads is less than equal to the number of user threads. So you have more flexibility and more concurrency with less overhead cost. So of course this does not completely remove all the problem. There are cases where the overhead is costly or where the threads can get stuck or something, but to a great extent it removes the issues we face because of many-to-one or 1-to-1. So this is the most preferred way of mapping user threads to kernel threads.